just fine.
Okay. So today is lecture 1 of Power Technology Fundamentals. So that's the Indian way of saying fundamentals, fundas. So, okay. So let me start. So battery technology is basically based on electrochemistry. So it basically falls in the no man's land. So it's right here. So chemists don't know electronics, electrical engineers don't know chemistry. So that's why this is a kind of difficult field. So the approach I'll take is that of fundas. So we will look at the fundamental aspects, real deep fundamental aspects of battery technology. And I don't have a syllabus which will develop as we move along, and I need volunteers to teach whatever they can. Okay, so let's get started. So let's go back to year 1800. So 1800, there were two blokes. One was Galvani, another one was Volta. They're kind of buddies somewhere in Italy. So Galvani, he took a piece of zinc, and I think he probably took copper. So I'm speculating right now. So he put a rag in between. He might have put sodium chloride in this space, let's say maybe in a beaker or something. And then he took two wires out, and he took a frog. That's a frog. And he connected the frog's legs, and the frog twitched. The frog moved. Now, this is pretty amazing that they thought that something would flow through a metal, that they needed a wire, and that this would produce some sort of energy. So Galvani didn't know that. So when the frog twitched, Galvani thought the frog had animal electricity. So I don't know if this is the first time anybody used the word electricity or not, but Galvani used it. And he also said the frog has electrical fluid in it. And that's why the frog is twitching. But he didn't know that there's electric current energy produced by the cell. So Volta was a buddy. Volta saw this. He went back to his lab. He said, no, I don't believe in this, So Volta came up with what's today called Volta's pile. So what Volta did was he took the same zinc metal and he put some sort of electrolyte. He probably used sodium chloride from his kitchen, and then he attached silver or copper, and then he connected a wire, and he could see joules, meaning heat, being produced in that resistor. So why is it called a pile? It's called a pile because instead of just using one of these, he played with adding more. So he put zinc over here, and then he put some more sodium chloride. He put silver over here. So now you see he has two batteries. Two cells, sorry. This one and this one. So this one battery has 2 cells, and you can keep on adding them. So notice, in between here, I did not put any electrolyte. If I put electrolyte over here, the output voltage would be 0, right? So you can't put electrolyte over here. So you can think about that why. And anyway, he added more and more cells. So you pile them up, and you could get different amounts of energy. So you could get more heat produced depending on how many cells are there. So I'm told that Volta's battery pile is still used, but we're not going into Volta's battery because I don't understand how it works, even though it looks very simple. So I went looking for understanding a simple battery. I looked in chemistry books, couldn't find it. So I went back to my favorite professor, Professor Erickson in University of Colorado. So he has a chapter on lead acid batteries, which is amazingly well written. So let me talk about lead acid batteries, because that's something you're familiar with because you have them in your cars. So lead acid battery. Now the reason why we're doing all this is we're developing the fundamentals of battery technology. So at some point we'll get to lithium-ion batteries, right? Okay, so let's talk about lead acid battery. So this is a very common technology, as you know. So you have lead. I'll draw it a little bigger. So here's a piece of lead, and it's porous to increase its surface area, and then we have a piece of lead oxide, PbO2, and we put this in a liquid. So I won't draw the beaker, but in between here, there's an electrolyte. And the electrolyte is sulfuric acid. So sulfuric acid gives you, of course, there's water over here. So the water molecules, water dissociates into H plus, and there's OH minus. So we'll discuss all this in detail. Right now I'm just summarizing it. And then there is SO4 ion in there. So there's water molecules. Of course, there's also H2SO4, etc. So this is electrolyte. And now lead and lead oxide are electrically conductive. So they have free free electrons moving in them. So they are mobile. Free electrons are mobile. Maybe I should put R over here. So metals, the definition of metal is a material that is electrically conductive. So we have this array of atoms in metals, and then we have in this C, we have a sea of electrons. So electrons are free to move as they wish. That's also true for lead oxide, but I'm not quite sure exactly. But the good book says electrons can also move in lead oxide. Okay, so the first thing I want to talk about is, okay, so let's mention that in this electrolyte, there is ionic conduction only. So electric current only moves because of the motion of these ions. Outside, we have the copper wire electrical connection. So that's electronic conduction. So any conduction from here to there, from here to there, has to switch from electronic to ionic, from ionic to electronic. Now, how does current flow through the electrolyte? It flows because these ions physically move. And they move, so conduction in electrolyte. What are the mechanisms? It's because of motion of ions. So how do ions move? One mechanism is called diffusion. The other one is called drift. So let's discuss this in detail. So today's lecture will be kind of hodgepodge, basically describing the basic physics of electrochemistry and battery technology. So let me discuss diffusion first. So diffusion of ions is their motion under the influence of concentration gradient. So you have, say you have J, which is the flux because of diffusion. So that will be proportional to concentration gradient. So if I have x distance on this axis and concentration of, let's say, H plus or OH or SO4, and let's say it's got a positive slope, so dc over dx is positive, the flux will be in this direction, right? So you have more ions over here, less over here. So by Brownian motion, you'll have flux in that direction, more than that direction, right? So you have to have a negative sign over here because flux is in the opposite direction to concentration gradient. Now, we also need a fudge factor over here. So we need a proportionality constant, and we call that diffusion coefficient. So D is diffusion coefficient. So let me not go into the units, or maybe I should. So flux, the diffusion is given as the units are grams per centimeter squared, meaning if you had an area, so you have diffusion through this area, so many grams per centimeter squared times second. So that's the unit of diffusion, and concentration is grams per centimeter cubed, and then I have x, which is centimeter. This could be meter. Probably in MKS we should use meters, right? So if I do the math, the units of diffusion are centimeters squared over seconds. So that's diffusion. So suppose sulfate ions are being consumed at the surface, so concentration goes 0 over here. Sulfate ions will move in that direction because of diffusion. If hydrogen ions are going this direction, they're reacting on the surface, the concentration is low on the surface, so hydrogen ions will go in that direction. Okay, so let's talk about drift. Drift is more complicated, so I'm going to spend some substantial amount of time on drift. So this to me is the fun part. So let's talk about drift. What is drift? So we're talking about drift of ions. Is their motion under the influence of electric field. So electric field causes drift. So now, so as I mentioned, this is a class on funders. So what is electric field? So before I can explain electric field, I have to explain what is a volt. So let's go understand what is a volt. So I'm going to talk about volt or voltage. So what is voltage? So suppose I have a conductor. I have point A and point B. Or this could also be an electrolyte. Let's call it electrolyte because we're dealing with electrolytes, right? We're dealing with the space between the electrodes. So maybe I should remove these lines. This is not a wire, it's an electrolyte. So the whole space is electrolyte. So what's the voltage between A and B? So what kind of experiment would you do? A thought experiment. And the thought experiment would be that voltage, or VBA, the voltage difference between A and B, is the work it takes to take a charge from A to B. So let's suppose I have a path like this, and I'm taking a charge Q. So I have a charge in my hand of Q coulombs, and we have to describe what a coulomb is. So I have a charge of Q coulombs. I take it from point A to point B. And the amount of work done is WAB. So definition of voltage is the amount of work, energy consumed in moving a charge Q from A to B, divided by, of course, Q. So it's work per unit charge. Now, energy is joules, right? And charge is coulombs. Energy could also be Newton meters, and charge is coulomb. So that's what a volt is. So voltage difference is the energy required to move from point A to point B, and what charge did you use for that thought experiment? The charge was Q. So you can say the voltage difference is the energy required to move a 1 coulomb charge from point A to point B. So that's the definition of volt. But we are after electric field. So what is electric field? So let's suppose I do the same experiment, but now I decrease the distance. Here the distance is a lot. I decrease the distance here to delta x. So the space, the distance from here to there is delta x. And let's say my voltage over here is delta V. So then from our definition, we know that delta V is equal to the delta energy it took to move the charge by delta x divided by our coulomb. So let's say Q coulomb. So we know that energy to go from here to there is the force, Newton force, times delta x, right? And of course, we have a Q coulombs. So we have a Q coulomb over here. That's the one we're moving from here to there. So now if you look at this expression, I can say delta V over delta x. And since I'm not a mathematician, I'm a poor engineer, I can say delta V over delta x, right? The gradient of voltage is equal to what? Is equal to force, which is in newtons, over charge, which is in coulombs. Now this thing over here is the electric field. I'll call this electric field. So electric field is voltage gradient, and it is also force per unit charge. So now, being an engineer, I don't worry about signs. So electric field is minus dV over dx. So that's because if I have voltage 1 volt over here, 10 volt over here, I put charge Q over here. In which direction will charge Q go? It'll go in this direction, right? So that's why it won't go in the right direction. That's why I have a negative sign there. So electric field is force per unit charge. Electric field is also the potential gradient. So in all these discussions, we assumed a few things. We assumed we know what a Coulomb is. Actually, we also assumed, well, what a voltage is. So why do we have 1 volt, 2 volt? Why do we have that magnitude? The reason is we go back to Volta. So when Volta built his battery, he took zinc and he took, let's say, copper, and he put some muck inside. He measured some voltage, right? So that's approximately equal to 1 volt. So that voltage he measured is of the same order of magnitude as a 1 volt. Now what about Coulomb? How did we arrive at the magnitude of Coulomb? And I think they arrived at that by, let's see, how did they arrive at that? So you have, so you have a definition. Volt is equal to joule over Coulomb. So they knew volt. So this is the voltage coming out of the Volta cell. That's approximately 1 volt. They had no idea about coulombs, but they knew joules. So joule is easy to measure. Even a poor guy like me can measure joules, right? Because I can take a beaker with 1 gram of water and I can put some element in it. And when it rises by 1 degree C, I know that's 1 calorie. And from calorie, I can convert to joules, right? So that's how they came up with the magnitude of joule, you know. Now, Coulomb. So it turns out later on they discovered that the charge on an electron is 1.6 times 10 to the minus 19 coulombs. So now you know that coulombs have how many electrons? That's 1.6 times 10 to the minus 19. That's for 6 times 10 to the 18. So 1 coulomb has 6 times 10 to the 18 electrons. So now that we have had a refresher in electrical engineering, by the way, for the chemists, this stuff I've shown on this page, none of my students at SUNY can do this. So it's amazing. Like, you can have 2 masters in electrical engineering and not know this. So this chart took me a whole weekend to prepare. So, okay. So now we have some of the basics out of the way. I want to do some chemistry. So it's not fair just to do electrical engineering. So let's do some chemistry. Let's talk about a water molecule. So we know that everybody knows H2O. So you could say H is bonded to O is bonded to H, right? But if you draw, so I'm drawing this in spatial correctness, meaning the 3 atoms are on a straight line. So if I draw it like this, this means that there is no dipole. So what is a dipole? Dipole is something that has a positive charge and a negative charge. So this has, let's say, charge Q, that has minus charge Q. So this, because of this this we know water molecule is a dipole molecule. Why? How do we know that? As IBMers, we know that if you have a circuit board, so this is a printed circuit board. Let's say you have a wire, copper wire, running through this, and there's a signal traveling. You're sending signals through this wire. What will happen is this electrical signal creates an electric field, right? And this electric field shakes this water molecule because it has a dipole. So depending on the electric field, this pulse going through, this water molecule will vibrate. So that slows down the electrical signal, right? Because if I'm sending a signal and the signal is making a molecule move, the signal is doing the work. So the poor signal is running a marathon, but it's getting tired because it's making these water molecules move. So energy is being spent by the signal. So we know water molecule is a dipole molecule. Therefore, we can't draw the molecule like that. We draw it like this. So now you see if there's charge on these, this charge, let's say is positive, this is negative, now we have a dipole, right? So it turns out they have calculated all this stuff, and this angle is 104 degrees. So water is a dipole molecule. So let's discuss, and water has high dielectric constant. So being a class of fundas, I have to also explain you what is a dielectric constant. I'll do that in a few minutes. But let's stay with the water. So water has two atoms, oxygen and hydrogen, right? So let's draw the oxygen atomic structure in simple means. So oxygen has 8 protons and 8 neutrons. So protons have the same, so P stands for protons and N stands for neutrons. So this charge is same charge as the electron, but opposite in sign. So proton has positive electronic charge, and neutron has no charge, but it has mass. So the way I've drawn it, oxygen atom has charge, right? But it doesn't have charge. Atoms have no charge on them. The net charge is 0. So I need 8 electrons to cancel the 8 protons. So I draw the first orbital. So now I have 2 electrons. So those little babies are electrons. And so I need to draw 6 more. So let me draw the second energy level. So this first ring I drew is called the first energy level. So the first energy level can only have 2 electrons. The second energy level has the rest of the 6 electrons. So I've drawn 1, 2, 3, 4, 5, 6. So over here, I don't have electrons. So now I have 8 electrons and 8 protons. So my atom is charge neutral. So turns out the second energy level can have 8 electrons. That's it, no more than that. The third energy level, which we don't have here, can have 16 electrons. Okay, so that's an oxygen atom. So now let's bring hydrogen atoms. So hydrogen has 1 proton only. That's it. The nucleus only has 1 proton. So it needs 1 electron. So I can draw the electron over here. So that's the hydrogen molecule. and there are two hydrogens, right? So let me draw one over here. So this is 1p, and its electron is over here. And let me draw the second one, 1p, and its electron is over here. So now notice we have one oxygen atom and two hydrogen atoms, and the oxygen second energy level is full. It can only have 8 electrons, so that's happy. And the hydrogen atoms are sharing the electron with the oxygen atom. So this is the structure of the water molecule. So the molecule can dissociate, meaning when we put this in water, some of these molecules will dissociate, and they'll basically I can cut them like this. In other words, H2O can become H plus plus OH minus. So this is dissociation of water. So a fraction of water molecules, a very small fraction, will dissociate. So notice that this one is just a proton. That's it. And this over here is hydroxyl ion, hydroxide. And the reason it's negative is it took the electron from this hydrogen atom. It just left the proton. So it left the proton, it took its electron, and this electron, that's making it negative. So that's why you have negative charge on the hydroxide ion, hydroxyl ion. So now I mentioned that water molecule can dissociate, but it dissociates only to some extent. So if I look at the concentration of protons and hydroxyl ions, this is symbol for concentration. They're both equal. So there's an equal to sign over here, and it's equal to 10 to the 7. So the units of this 10 to the 7 always confuse me. But we know that pH is minus log hydrogen ion concentration. So that's equal to 7 because log of that is 7. So a very, very small fraction of, oh, sorry, this is minus 7, and I think the concentration is molar. What that means is moles per liter, per 1 liter, and mole is molecular weight of the substance in grams divided by liter. So that's the concentration. I forgot this negative sign over here. So that's why minus log hydrogen ion concentration is 7. So pH of pure water is 7. But even pure water contains very few protons and OH ions. So that's the story on water. So let me talk about sulfate or sulfuric acid. So sulfuric acid kept me awake many nights. So what is sulfuric acid? And it drove me crazy until I read that Linus Pauling had the same problem. And Linus Pauling is only a little older than I am. So maybe I'm in good company. So what's the problem with sulfuric acid? The problem is, how do you describe the structure of sulfuric acid? So sulfuric acid is H2SO4, right? So we already described hydrogen atom and oxygen atom. So let's describe the sulfur atom. So sulfur has 16 protons. So this is a heavyweight, and 16 neutrons. So that's the nucleus of sulfur. So now we need 16 electrons to neutralize the 16 protons, right? So as we just learned, in the first energy level, we can only have 2 electrons. In the second energy level, we can have only 8 electrons. So I've drawn 4, 5, 6, 7, 8. So 8 plus 2 is 10, so you're left with 6. So this time, that's the third level. I'm going to draw the 6 over here just to make my life easy. But they're kind of distributed all around. So I'm just drawing this billiard ball model. In reality, it's not like this, right? So that's the sulfur atom, and it has a what we call +6 oxidation state. What that means is it's got these 6 electrons. It can get it doesn't like them. They're hanging around doing no good, so it can get rid of them. So it can get rid of +6 electrons. So its oxidation state is 6. Now let me redraw. Do I have to redraw? Okay, that's the oxygen atom. And remember, we talked about that it only has 6 electrons on the second shell. So this has a -2 oxidation state, which means it wants 2 more to become happy. So atoms are happy when they're full, like neon, helium, their shells are full. So oxygen is a mean, angry atom because it's greedy for 2 electrons. So it's ferocious. So is hydrogen. What happened to my hydrogen? So hydrogen has 1 electron. It needs 1 more. So hydrogen is a mean atom too. So when 2 means come together, they clash, they combine, they form water molecule. So let's get back to sulfuric acid. So we have sulfur, we have oxygen, and we have hydrogen. So they have to combine. So I thought a lot about this, and I struggled. And so I start with the sulfur, and sulfur has 6 electrons on the outside. So what sulfur does, it says, okay, oxygen, you need 2, I'll give you 2. So sulfur gives oxygen. So these lines are electrons. So this line is an electron. So sulfur gives oxygen 2. So this oxygen is happy, but then there are more oxygens around, so it has 6 to spare. So it gives another 2 to another oxygen. So this oxygen is happy, this one's happy. Now it's only got 2 left. So why not just give 2 to another oxygen and just stop here? But it's beyond my intelligence why it gives it to 2 of them. So it's making trouble. So instead of giving those, it had 6, it gave 2 here, 2 there. Instead of giving 2 to this one, it decides to split. So now these poor oxygen atoms are hanging around with only 7 electrons. It got 1 from here, it had 6, it has 7. So it needs 1 more. So these oxygen atoms are going crazy, so they find each a hydrogen atom. So this is the structure of sulfuric acid. Now, is this truly correct? Of course not. This is like a approximation, right? So this is H2SO4, and this can dissociate into H plus H plus SO4 minus. So how does it dissociate? It dissociates by being, if I cut the molecule over here, this proton, see, this is the electron, this is the proton. So here's the proton. It's got a positive charge because there's no electron with it. So in other words, if I remove this electron, now this becomes a proton, right? That's that. So these are protons. And the reason this is a charge of -2 is because of this and this electron. The two electrons that came from the two hydrogen atoms makes the sulfate ion -2. So I think we're done with the chemistry part of it. So we have described the motion of ions in the electrolyte. We have described the sulfuric acid and water. So we know where this sulfate ion comes from. We know where a proton comes from and where the OH comes from. So I have 10 minutes left, but people say that students can only concentrate for 40 minutes. So we're approaching 40 minutes. So I want to discuss something interesting. What is a coulomb? So if I give you 2 coulombs, 1 positive coulomb and 1 negative coulomb. If I ask you to do this experiment, expand these coulombs like this, question is, how much energy will it take? Come on, and Mike.
I have this room reserved for 3 o'clock for the data center.
At 3 o'clock.
We got a vice president from an outside company.
We will welcome the vice president. So there are 2 coulombs, a positive coulomb and a negative coulomb. So you stretch them out. The question is, how much force does it take? So let me do that calculation. But before that, what I want to do is to talk about a law of electrical engineering. So electrical engineering is based on 4 laws that Maxwell wrote. So these are Maxwell's equations. So Maxwell, I think that's how you spell his name. So Maxwell took already existing laws and he just summarized them. So one of them is called Gauss's law of electricity. So what I'm trying to do, so let me just explain to you where I'm going. What I'm going to explain is that charges cannot get localized. In other words, positive charges cannot separate from negative charges. So the charge concentration in nature is homogeneous. So this table, wherever you look on the table, the charge concentration is uniform. When charges segregate, so positive charges come over here, negative charges come over here, and you're playing golf over here, what happens to you? Lightning. So nature doesn't like separation of charges. So the question is why? So that's what I'll try to explain to you. But I need to explain what is Gauss's law of electricity. So Gauss's law of electricity says that wherever there's a charge Q, there's electric field, right? So if the charge is positive, there'll be electric field like this, right? Radiant electric field. So we know what electric field is, right? We described electric field is the force on unit charge. So if I need to know, because of this charge Q, what's the electric field over here? I put unit charge here and I measure the force in newtons. That's the electric field. So what is this Gauss's law of electricity? So let me draw a spherical surface. And so this is a spherical surface, right? Gauss's law of electricity says that a charge Q enclosed in a closed surface is equal to the dielectric constant. So here comes the dielectric constant. Of this media. So this air or whatever liquid has a dielectric constant. And we integrate over the surface, the spherical surface, and what do we integrate? We integrate electric field times ds. So on this surface, I take an element ds, I have electric field E, so I do E dot ds, and I do the integration. For this case, it's very simple. So the integration is dielectric constant, and the area is 4 pi r square, and I have electric field, right? Electric field is uniform because the distance is same everywhere, right? So my electric field becomes equal to 1 over 4 pi r square. Well, let me put the dielectric constant, and I have Q over the radius square. So we have derived the electric field anywhere on the circle, right? So now we are talking about, in our case, we have 1 coulomb here and 1 coulomb here. What's the force between them, right? So we know electric field is force divided by charge. So this is another charge. So I'll call this Q1, I'll call this Q2. So force is equal to Q1, Q2 over 4 pi epsilon r square. So this is the force we are after. So this is the force we're after. And in air, the epsilon is 8.85 times 10 to the minus 12. The units are coulombs over Newton meter square. So if you plug 1 coulomb here, 1 coulomb over there, radius of, let's say, 1 centimeter, and you plug this number in there, this comes out to be 10 to the 14 newtons. So if I have a positive charge on one hand, negative charge on one hand, it takes 10 to the 14 newtons to pull apart these charges. So now you might say, what the hell? What's 10 to the 14 newtons? Is that a big number? So let me explain to you what a newton is. If I take, here's my gem, if I take 1 kilogram of my weight and I try to pick it up, how many newtons would I need? So force is mass times acceleration, right? Mass is 1 kilogram, acceleration is 9.8 meters per second square, so I need 9.8 newtons, so about 10 newtons. So this is like lifting 10 to the 13 kilogram weight. So that's how much force it takes to pull apart 2 coulombs. Now coulomb is a very small charge. So suppose I ask you to electroplate some zinc or aluminum. By the way, all aluminum that you buy is electroplated. So you start with, I think, aluminum hydroxide or something, and you electroplate the aluminum out. So aluminum's atomic equivalent weight, I don't know what it is, but let's say, just for the fun of it, is 20 grams. So 20 grams of aluminum to electroplate would require, so let's not go too far, but typically you need that many coulombs to plate out 1 equivalent weight of metal. So ballpark figure, you need 96,500 coulombs to get a little bitty piece of metal in your hand. Now, and I just described to you what 1 coulomb can do. So just imagine if I had 1 coulomb over here, 1 coulomb over there, and I let go, the amount of energy released will vaporize all of Poughkeepsie. 1 coulomb, you know. So on that bright note, I'll stop. Thanks, guys. Let's call it a day.